So did anybody try to read this before came to class? Math. What kind of math classes have you had? Basic math? Anybody had algebra? Okay. So if you had algebra, you were introduced to graphing. Remember the Cartesian coordinate system? Okay. That's where we're going to start. Cartesian coordinate system is it's a two-dimensional array. We subdivide the piece of paper into 4 quadrants. And this line here is called the abscissa. Did I spell that right? I think I spelled it right. And this one is called the ordinate. Right? Abscissa, ordinate. And if we just focus on one line at a time, actually both lines start at 0. This is 0 for both lines right here. So for the abscissa, or sometimes we call it the x-axis, and this we call the y-axis, start at 0. This is all positive. Those are positive values. These are negative values going in this direction because we start at 0. That means these are negative values and these are positive values going that direction. If we just stayed on the line, we could say, how far am I from the origin? All right, move out here, say 1, 2, 3, 4, 5. Move out here to 3. So that's where I'd be. I'd be 3 units from the origin. But what if I were on this line? 1, 2, 3. If I were, say, 4 on this line, right there. There. But suppose I have a measurement that has 2 components to it. Say I'm measuring a gas, a confined gas. I'm measuring its volume when I put pressure on it. So you know what happens when you put more pressure on a gas, it shrinks, right? So if I put, say 1 atmosphere pressure, it might be 10 liters in that space. If I put 2 atmospheres pressure on it, it might only be 5 liters, right? If I put 3 atmosphere pressure, it might be, let's see, 3.33 liters, so forth. So now we have 2 numbers that are related to each other. At 1, it's 10. At 2, it's 5. At 3, it's 3.33. Okay? When you have 2 numbers related like that, you can put them on this system. One of them would be related to that direction, and the other would be related to this direction. And if we say, well, I made that too big. I've got to go up to, I got to go up to here for 10, right? So if we have 1, then I'd put it right here. That represents 1 and 10. If this is pressure and this is volume on that axis. So now we can graph 2-dimensionally. If we're only on the line, that's 1 dimension. If we're in this space, then that's 2 dimensions. Okay. Let's see. If I had 2 here, I'd go down to 5. Right here. If I had 3, I'd go down to 3.33, right about here. And you could keep going. But each one of these is designated by the X and the Y value. So this would be 2, 5, and this would be 3, 3.33. All right, in the sciences, when we graph things, and when these values originated with an experiment, these are measurements. These are measurements, and which one did I control as the experimenter? That one. I controlled the pressure, and the response is the volume. So the one I controlled is the independent variable. The independent variable is always on the x-axis. That's why I put the pressure down here. And the dependent variable is the one that responds to what I do. That's on the y-axis. Okay? Independent, dependent. Let's see. Yeah, I did spell it right. Now, most of the time in the sciences, we spend in this region, in the positive. But occasionally we go over here into the negative positive region. We'll have an example of that in just a few minutes. They label it A, B, C, and D, clockwise, A, B, C, and D. I don't reference them that way, so you don't have to pay attention to that. All right. So here's an example where we have, on the x-axis, we have temperature. This is of a confined gas. We have temperature under constant pressure. And if we change the temperature, what happens to the volume? Goes up. When we study gases, that'll be known as Charles' law. The variation of volume of a gas with temperature. Notice that the units, when we let me see, let's clean this up a little bit. Okay. Now we've got temperature on this axis in Kelvin, right? So what that means is this temperature can never go below 0 because Kelvin starts at 0. And this one is the volume in liters. Yeah, in liters. Notice we label the axis. What does the axis represent? And then we have units, right? In this case, we got, let's see, 50, 100, 150, and so forth. And on this one, we have volume of 0.2, 0.4, 0.6. Yeah. Okay, I have a bone to pick with the authors of this method, this experiment. Notice that they put a point out there in front of each one of those, right? We understand that to be a tenth because there's nothing else around it. But if you put that in a sentence, you could mistake that period for the end of a sentence, right? So that's why I call those orphan decimals. What you need when you have a decimal out there is a 0 on the left of it, right? To confine it and tell you that that decimal is part of a number, not part of the sentence. Right? I don't like orphan decimals. If you learn to write orphan decimals in grade school, forget them. Write them my way. So this would be 0.2, 0.4, 0.6, 0.8. Okay. And then there were data points drawn in here. I'm not going to put them in exactly the right place. Something like that. These are actual data points, X, Y values, X, Y, X, Y, X, Y. And you can draw a straight line with these. It looks like it would be useful to put a straight line in there. This is a best fit curve. Now, best fit curve covers straight lines too. So if I put something in here like this, what you try to do is minimize the variation from your line to the points. So let's see, I want to get about the same distance, something like this, to where they're on either side of the line about the same distance. Try to minimize the variation. That's the key to drawing a best fit curve. Now, if it is a real curve, how do you do that? There's a device. If we're doing this by hand, there's a device called a French curve. Anybody ever seen a French curve? Now it's made out of plastic. It's a transparent piece of plastic, and it's got a curve on it that's decreasing radius. So it'll start like this, and it'll go like that. Something like that. So you've got different radii of curvature. So if your points go like that, then you can rotate this around and match the curve to the points. We don't use that much anymore because computer programs do a better job. But for our purposes, since we're doing it manually, that's what you would use for best fit curve. Okay. As long as you're inside the data points, you can take any one of these places on that best fit curve and say, what if? What if the temperature were 125, right? We don't have a point for that, but now we have a best fit curve. We can say, if we go up here like that, then we can say, that's what we expect the volume to be. Okay. Anything in here using that method is called interpolation. Okay. And it's very well confined by the data points. So you can expect to reasonably come out with good numbers if you say what ifs. If you go outside that data region and say, I think it's going to continue like this, right? These are both, either end is extrapolation. You can use extrapolation if you're really careful and you understand that you don't know what's going to happen outside this. It could go like this. It could go like that. Who knows? We don't have data points to confine it. So just be careful with extrapolation. Notice the other things about this graph. When you draw your graph, the first rule in producing a graph is the graph must stand on its own hind legs. It's got to stand alone. It's got to be interpretable by any reader outside the text that's around it. So it has to have a title to say what it is. It has to have a system, in our case, a Cartesian system. It has to have labels on the axes to say what the measurement means. And it has to have what we call tick marks to mark off the values that are assigned to it. Right? It needs all those components. Sometimes we even put comments underneath if we need to say something more about the graph, just so that it can stand alone. I forgot to mention this in the beginning. Why do we even bother with graphs, right? Can we just make a table of numbers and say, here it is? If you have a small table of numbers, yeah, you can do that and make reasonable sense of it. But if you have a lot of numbers, your reader's eyes are just going to glaze over. So when you put a graph, when you put data into a publication, you're trying to convince your readers that your interpretation of the data is correct. Okay. And one of the ways to convince your reader is visually. Right? Humans are visual creatures. We need to, we can make sense of the world better through images rather than raw numbers or any other methods. So graphical representation, and this Cartesian system is just one possibility. They're just, the sky's the limit. We can even graph three-dimensionally now. With our computers, it's easier to do and get an idea of three variables that are working to produce that graph and produce not just lines, but surfaces. But back to the topic. So that's what you need. When you present a graph, that's what I'm looking for. A title, labeled axes marked off in equal units, right? Notice that when we go from on the temperature, 50, 100, 150, those are equally spaced. Right? And then the subunits from 50 to 100, you've got 5 squares. That means each square represents 10, right? 50, 60, 70, 80, 90, 100. If you try to set it up so that you've got equal numbers, decimals are better. If we go from 100 to 200, those are 10 squares. So 1/10 of 100 is 10. Each square is worth a 10. What I'm saying is you don't go, you say, all right, I've got data, I've got a point for 50, and then I got a point for 100, then I got a point for 300, then I got a point for 600. That's unequal distances. It doesn't work that way. Right. In this system, the way we've set it up here, this Cartesian system, they have to be equal numbers between each one. Otherwise, you're just going to get a wonky, useless graph. Okay, so you'll notice that in your graph paper, you have major and minor lines, right? Grid marks. The grids are the lines. So you have major lines here and minor lines here. That's to visually help you count. All right. Those numbers are called scale units. Right? So the scale units here are 50 for every 5 units, or 10 for each unit, for each mark. Those are scale units on the grid. The grids are the lines on the graph paper. Then these data points are represented by X and Y values, right? The independent variable and the dependent variable numbers. Best fit curve. Okay. Now with this one, notice that as the temperature increases, the volume increases. So when the line moves this direction, lower left to upper right, that's known as a positive slope. And that's a direct relationship. Is a positive slope. So is anybody familiar with this? Right? The basic formula for a straight line. Right? You can find y if you know, if you put in x and you have a value for the slope and you have a y-intercept. In this case, the y-intercept is 0, so that would go away. And you just have a slope times x. So if we know the slope times the x value, we can find out what the y value is. Okay? How do you find the slope? The slope is, say you go from one point here to this point, and it doesn't have to be a measurement. You can pick it from your best fit curve. And you go over how much did it move on the x-axis and how much did it move on the y-axis. This is change in y. This is change in x. Okay? So the slope is equal to the change in y divided by change in x. So if we know it changed this much, then it has to change that much in y. That would be that value right there. So if this is K temperature and liters, then the units of measure would be liters divided by K. That would be the slope, units of measure. Right? We don't just put numbers in here, we put the units too. Right? Everything you do to the number, you do to the units. So we divide the numbers, we divide the units. That's the slope. And as long as this is positive, you have a direct relationship. If, on the other hand, let's see, you have a, I'm looking for, oh, well, there's the calculation of the slope. If, on the other hand, you have a nonlinear relationship, like this one, pressure and volume, like I showed you earlier. If we say this, I change the pressure and measure the volume response. What you will get, this is the origin, what you will get is something like that for our gas. That's in mathematical terms and geometric terms, it's called a hyperbola. Characteristic of a hyperbola is this tail goes out here and never touches the axis. This tail goes up here and never touches the axis. But anywhere on that line, as the pressure increases, the volume decreases. Right? This is an inverse relationship. Now, since this is not a straight line, we can't calculate a single slope for that line. But any point on that line we can draw a tangent to that point. Tangent. You know what a tangent is? It's where the straight line touches the curve at only one point. Okay? And there's a slope for each one of these. Notice that they're all negative. Right? This is a positive slope. That's a negative slope. So when you have a negative slope, you have an inverse relationship. And we've got our pressure marked off and our units marked, our volume is marked off, drawn our points and a best fit curve. Let's see, before I do that, let me go back up and see. I want to see if I missed anything. Inverse proportion, yes. Calculate the slope of the straight line, yes. Let's pause for a minute and say, all right, so you're given a set of data and you're expected to draw a graph, right? So what are the factors that you need to consider when you're going to put those numbers, those pairs of numbers, X and Y, on that paper to make the best looking, the most useful graph? Well, you look at your X and Y's values and say, which one covers the most distance, right? From the lowest to the highest. and you've got a sheet of paper that's 8.5 by 11. So one side's shorter than the other. You want to use the longest side for the greatest span of numbers. Right? So if you do it like this in portrait mode, right, and draw your graph in like that, the greatest span is going to be the y's. So if the y is the greatest span of numbers, you're going to use portrait mode. But if x is the greatest span of numbers, you want to rotate it into landscape mode. That puts x down here with the greatest span. That's the first thing you do. And like I said, with computers, it doesn't matter. Then what do you want to do? Well, you want to take your list of your distance of numbers and say, how do I get those numbers spread as far on the axis as possible? You want to spread, you want to use all your space, right? So you say, all right, if I mark off, if I've got to go this many, this many, this many, and I'm done, it looks like you've got room to put more out there. So just double your unit span and put them all the way out to here. That spreads them out. You want to spread them out as far as possible to cover the most space on your graph. Because if you're going to use that graph to interpolate, then it's easier to interpolate from a large curve than it is a small curve. Right? If you draw your graph like this and you got points like that, I'm done. How are you going to use that? It's a mess. So you portrait landscape first, and at the same time you figure out your grid marks. Where do you want your marks to be? So that's tilting your graph, best straight line, plotting the data points. I know, because I've got a question in here. I think, if anybody's looked at it already, let's go down. I'll come back to those in just a second. All right, these are definitions. You can find those in the text. Let's see. All right, what 5 items must you consider when selecting the size and range of scale units for X and Y axis? Well, you got to decide if it's portrait or landscape. Then you want to get all your numbers on the scale with covering the maximum distance. And at the same time, then you're trying to figure out where you put your grid marks and the numbers that you apply to them. Let me see. I'm forgetting something, I know. Oh, you got to know what your unit dimensions are. Right? Those come from your data. The unit dimensions are going to be here like pressure and volume. And then what are the size of your units? Right? Is it going to be millimeters, kilometers, liters, grams, kilograms, whatever? Orientation. What's the maximum range that you can fit in there, which also fits into orientation, portrait or landscape. Then you want to know what your scale units are. Right? What am I going to make them? 50, 100, 150, or do I make them 100, 200, 300, 400? What are your scale units? And then at the same time, you're looking at what are these subdivisions? Right? Because if you're going to be using the graph for interpretation, you'd like to have a decimal relationship here, if you can get it. So if you go 10 units from one to the next, that means it's a tenth, right? Just, it's easier to read them if you're in the decimal system. I think I mentioned 5 there, didn't I? All right. So let's go back because I know I missed some stuff up here. Here we go. Okay, so there's where we were with our pressure volume. Let's come over here. I'm going to steal a little bit of my thunder down the road. When we measure pressure versus volume, this is an expression of Boyle's law. And Boyle's law simply says that pressure times volume equals a constant value. And that always gives you a hyperbola. When you have a variable times a variable equals a constant, this product equal a constant is always inverse. Because if that's constant, then when this one goes up, that one has to go down in order to keep that constant. Whereas Charles' law was volume divided by temperature is a constant. So when temperature goes up, volume has to go up in order to keep that a constant. So when the quotient is constant, it's direct relationship. When the product is constant, it's an inverse relationship. Right? That's what we see here. But scientists don't like curves. If we can get away from them, if we can transform the data and make a straight line, that's where we want to go. So in the next part of this graph, we take the same data, and I'm going to show why that works using Boyle's law. Mathematically speaking, if I divide both sides of the equation by the same unit, I haven't changed it, right? That's allowable. If I divide both sides by volume, that's good. This one cancels, right? V cancels V. And this one, now we've got V equals K over V. Well, I want to factor that out. I want to keep K in the numerator times 1 over V. So what does that look like? Y equals mx. Now I have a straight line. All I have to do is take the inverse of volume, plot that against pressure. So let's see, if I take that data and transform it, now I can draw. I still have pressure is the independent variable, and it didn't change. But now I have 1 over V on this axis. What are the units of measure? I took the inverse of liters. So the units of measure now are liters to the minus 1. Right? 1 over liters. This one's still, what, atmospheres? Okay. So now if I plot this data, it's going to go like that through the origin because there's no y-intercept here. It goes through 0. That's how I get a straight line. And that's why this straight line right here on that graph, that's why it looks straight. Because now we're not plotting pressure volume, plotting pressure against inverse volume. But all the other things hold. You still have to say, all right, once I've got my data, is it portrait or landscape? I have to label my axes. I have to find out, all right, what's the units that I'm doing? Actually, you've already done the x-axis because you didn't change it at all. So the x-axis is still the same as before. Now you have to do the y-axis in inverse units. So you have to look at that one and say, all right, how am I going to get these in here? And use up the greatest space and make the subunits decimal if possible. And these two graphs were based on the same data set, only the second one was transformed. Volume is inverse volume now. That gives us a straight line. Now, if we use this, let's say it's easier now to say if I change the pressure and I use a pressure that's not in the data set, right? And let's see, is that showing up? Yeah, sort of. If I use a pressure that's say in here, and now I know what's the inverse volume going to be, it's going to be over here somewhere, like 0.048, 0.048. Inverse liters. All right, I want to know what the volume is at that pressure. That's not it. We have to take the inverse of that and give us a number. So if we take the inverse of this, and I'm back to liters, and whatever 1 divided by 0.048, that's the value that would show up over here. Okay. All right, here's some other nonlinears. We're not going to spend a lot of time with those. One possibility, right? This one uses the inverse, but it doesn't work. Only when we take the common log of the value does it give us a straight line. Right? And we're not going to go into that much detail. I just illustrated the difference between curves and straight lines as a possibility. I will mention this, though. We're going to get into something here that's not as important yet. It's a titration curve. Let's go down. Notice that we're starting off with a required section worth 78 points. And there's a bonus section, right? You can take it or leave it, right? If you feel adventurous, you can work on the bonus section. And the bonus section, let's see, where does it start? And keep going, keep going. Here it is. The bonus section uses this data, and it's going to plot out like volume of base added in milliliters. And then what we're going to get over here is pH. Anybody know what pH is? It's an expression of acidity. Right? Lower pH is more acid, higher pH is more basic. Right? We'll get to that later. But when you plot the numbers, they're going to go like this, like that, and like that, and like that. Gives you a sigmoid curve. So if you plot that data, you're going to get something that looks like that, but you still plot it the same way. I mean, you still set up the graph the same way with those 5 conditions, and then answer these questions. And that's extra credit. That's a bonus section. And then let's see, if we get down to this set of data, we've got time and temperature. That is going to give you a broken curve. In other words, you've got a nice section here, and then all of a sudden goes up here. That's a broken curve. And there's some questions to answer there. Some students in the past, they've just answered the questions by looking at the data and not drawing the graph, which is fine. It's fair, it's a bonus. You can try it or not. But that's extra, and this is where the required section stops. I think there are 1, 2, 3 graphs, I believe. 3 graphs. We have one for volume and temperature here that you draw. And then we've got pressure volume, gives you that hyperbola, and then take the inverse and draw the second one, and that gives you a straight line. So you have 3 graphs required, and the rest is extra. Okay, any questions? I've been talking the whole time. I've seen some nodding heads and some glazed eyes. So why am I putting you through this torture? Because down the road, we're going to draw some graphs with data that we collect in the lab. So you need this experience. It's not quite as rigorous in this course as it is for my afternoon class. Right? They get the full 9 yards. Or 2 semesters if they're brave enough to come back for the second one. But this is something that you can always carry with you. And then doing it by hand first gives you an idea of what's actually going on, what has to happen. And then if you get to the point where, say you work for somebody, you work for an employer that uses computer programs to draw out your graphs, then so much the better. But now you understand why they do it that way. So we do it the hard way first, and then you can automate it later. Or if you work in a, let's see, there were some MLTs, right? Here. You might run across a situation where an analysis in your lab plots out a curve. It's possible. And then you know how to interpret it. Okay,